Swayam Prabha. Digital India. Educated India.
Welcome to Measures of Green Urbanism. Today we are going to start with lecture 18. This is the lecture related to 4th week of this course, and today's topic is connectivity. So, as we have discussed in the last lecture, accessibility is focused on the ease of reaching a destination or reaching a destination with respect to time, distance, cost as important factors that impacts the measure of accessibility. Connectivity is a network derived measure. So, connectivity can be measured with respect to air based connectivity, water based connectivity, railway network and road network. So, in railway network and in road network, we have a very tangible network which can be measured directly. In terms of water based connectivity measure or air based connectivity measure, we are more focused on the frequency of services. So, when we are looking into network analysis, it provides us a measure of accessibility and connectivity, and also allows us to compare different areas, different regions as well as different countries. So, in a network analysis, we essentially represent different locations as nodes or vertices, and the links or the edges between these locations or nodes. So, the overall representation is based on, we can calculate the distribution of these links as a way to look into the overall level of network that is being developed, and as well as there are other measures such as looking into the spread and diameter of a network, looking into density of a network, the ratio of edge to vertex or edge to node of a network, the number of path or alternative routes that can be measured or that is present in a network, and centrality. So, we will be looking into these aspects in details in the next slides. So, in a transportation network, transportation systems are commonly represented by using their or representing their structures and flows. So, a transportation network denotes either a permanent track, which is rail, road, canals, etc., or it represents a scheduled service such as airline, public transit, trains and their frequencies. So, Metcalfe's law states that the value of a network is proportional to square of the connected nodes, so that the complex networks are exponentially more valuable than simple network. So, in a complex network, in a simple network actually, the number of edges are nearly equal to the number of vertices. As the number of edges increase in a network, it gradually becomes more complex. So, in here with respect to Metcalfe's law, we find that the overall value of a network is dependent upon the square of the connected nodes, whereas is size of a network and n is number of nodes. And a route is typically a straight single link between two nodes that is part of a larger network, and this route can be tangible routes such as roads and rails, or less tangible routes such as air and sea corridors. So, within the transportation network, we often evaluate the network structure, and network structure can vary from a centrifugal network to a centripetal network, from a more uniform network to a more concentrated network. So, in a centrifugal network, different locations are accorded almost similar importance. There is no fixed center in there as such. On the other hand, in a centripetal network, certain locations are given much more importance, and there is definitely a very easily identifiable center in case of a centripetal network. Centripetal networks are relatively less resilient than centrifugal networks, because in centripetal network the number of edges in response to the number of vertices are bare minimum. As well, in case of centrifugal networks, we often see that the number of edges are either equal to the number of vertices and is usually much more than the number of vertices. So, it allows for alternative routes being present. Efficiency of a network represents its ability to support flows particularly during disruptions. So, usually under operating conditions, there are lot of disturbances or a lot of limitations created by the different right of way that is available, different kind of traffic densities that impact different segments of a network. So, overall the efficiency of a network will depend upon how it can support the flows at under operating conditions, and while it meets certain performance criteria in regards to speed, capacity and safety. So, a certain part of this can be measured very objectively by looking into connectivity measures. The efficiency of a network also depends partially on the layout of nodes and links, which is commonly known as topology. So, which is a scale-less measure, and efficiency is also related to resilience, the ability to support disruptions while maintaining a level of service and connectivity. So, if the number of edges in a network is higher than the number of vertices in a network, it commonly means that it has the presence of cycles or circuits within it. At least it has alternative routes available, that makes it more resilient. So, common index which measures efficiency is one such common index is a detour index, and it actually measures the efficiency of a transport network in terms of how it overcomes distance or friction of distance. The closer a detour index gets to 1, the more efficient is the network. Other measures of network efficiency is network density, which looks into the overall length of the network in terms of, if it is a road based network, then overall road length in kilometers per square kilometer of surface area. So, the higher this value, the more developed the particular network. In many cases, we also calculate intersection node density. So, number of intersections per square kilometer of an area. So, moving on. So, graph theory is essential in evaluating connectivity of any network. So, in a graph theory, a graph is basically represented by set of vertices which are connected by edges. So, in the given graph, we have two graphs present in here. In one there are 8 vertices, in the other there are 7 vertices. In the first graph, that is a connected graph. In the second one, that is not a connected graph. So, all nodes are not connected in here. In the second graph, we have actually 2 subgraphs. So, if we look into the second graph, where we have the nodes 1, 2 and 3 as one part of as a subgraph and this as the second subgraph. So, a complete graph is one where all nodes are connected, and it usually means that all nodes in that graph are connected with every other node. That is the complete graph. But in a complete graph, usually we find that all nodes are always connected. So, a graph where all the intersections of two edges end up in a vertex, they are known as a planar graph. And typically in urban areas where we have bridges, where we have underpasses, they are not exactly planar graph. We cannot represent them typically through a planar graph. So, a sequence of links that are traveled in the same direction is known as a path. So, in here if we see 1 to 2, 2 to 4 and then 4 to 8 is a path. So, these are the common definitions in terms of graph theory. So, a sequence of links having a connection in common with one another is known as a chain. So, in this graph we have a number of such chains. So, we can have one chain which is connecting all the edges. So, we can actually generate a minimum spanning tree which will also be a chain with respect to this graph. So, a chain where the initial and terminal node are the same and that does not use the same node twice is typically known as a cycle. And a cycle where all the edges are unidirectional or move in one direction only are known as a circuit. So, in here for example, 1 to 2, 2 to 3 is actually a circuit, 5 to 6, 6 to 7 and then again 5 is also a circuit, whereas these are cycles. So, if we look into the graph theory, there are different measures depending upon whether we are measuring the overall network or whether we are measuring the node based, we are looking into individual nodes. So, when we are looking into network based measure, the first measure that comes up is looking into diameter of a network. So, the diameter of the network is denoted by length of the shortest path between the most distant nodes of a graph. So, in here if we look into the first graph, we find that this being a symmetrical graph almost. So, in here the diameter is 2. In the second graph we also find that though this graph has no specific center or something that can be identified as a center, the diameter is 3 looking into the distant node. It is easier to calculate this because the second graph is also a symmetrical graph. In the third graph, it is relatively difficult to measure, to identify the center of this graph at one go, but we can see that the two distant nodes can be 1 and 9 and thereby the diameter of this graph is 4. Next, we will look into another measure at network level, which is the number of cycles in a graph. If a graph has more number of cycles, that means it has alternative paths. So, in a way it is more resilient. A graph having or a network having alternative paths, a network having more number of cycles are more resilient form of network. So, trees and simple networks have no cycles. So, minimum spanning tree has no cycles. So, in the first graph, so we have in here 4 graphs A, B, C and D. In A, we have 2 subgraphs. So, in A actually we can see that the number of cycle is 0. So, number of cycle can be measured by counting the number of edges, the number of vertices as well as the number of subgraphs. So, in A we have two subgraphs, whereas in B, C and D there are no subgraphs, there is only one graph. So, they are all measured as 1. So, in B we have one cycle which is identified in here. In C we have 3 cycles, and in D we have 5 cycles. So, D as a network is much more resilient because there can be alternative paths connecting distant nodes. The next measure we are going to look into is pi index and eta index. So, pi index actually looks into the relationship between total length of the graph and distance along its diameter. So, in the previous slide we have already looked into how diameter of a network is measured. So, in here it is basically telling us about the whether each location which is represented by a node are having more importance with respect to other nodes, or they are having equal importance. So, in the first graph, as we see that pi is actually 3, because pi is looking into the overall length of the network as divided by diameter of the network. So, in both graph 1 and graph 2 we have the same we have basically same number of edges, same number of nodes. In graph 1 we can see it's a centripetal type of a graph. In graph 2 it has a centripetal framework as well as peripheral connections. So, in graph 2 the length is more, so the pi index is more. So, when we compare these two graphs we see that the eta in both of these graphs what changes is the overall length of network. So, the pi index increases in here. In the third graph the pi index is actually little more than in case of a centripetal network, but otherwise it is much lesser than the second network. Eta index looks into the average length per edge or link in a graph. So, in case of more developed networks the value of eta is less. So, a low eta value represents a more developed network. So, if we look into the second network, if we compare between the second network and the third network, we see that value of eta index is lesser in case of the second network. In the second network the overall the eta index is less. It is in here again the locations are more uniform, are of uniform importance, and while pi index is larger, yet when we look into the combined impact of pi index and eta, we find that the second network is having better performance. Next we look into the alpha index, which are again common measures at network level related to connectivity. So, alpha index actually measures the number of cycles existing in a graph in comparison to the maximum number of cycles that is possible in a graph. So, an alpha index the value ranges between 0 and 1. So, in here we see that in case of graph A, where there are subgraphs and where there are no cycles present, the value of alpha is 0, and in case of D the value of alpha is 0.55. So, if more number of edges are introduced, say between 0.1 and 0.7 or 0.1 and 0.6 and so on, we will find that the overall alpha index will keep on increasing. In case of beta index, which is another measure of connectivity at network level, we find beta is basically looking into a comparison of number of edges in a graph in comparison to the number of vertices. So, the higher the value of beta, the more complex the network. So, in here we see that in case of beta index, it does not have an upper limit exactly. So, in case of the subgraph or graph A, the beta value is 0.71, the alpha value is 0, beta value is 0.71, but the beta value is 1 in case of graph B, and it keeps on increasing till 1.57 in case of D. Gamma index is the third index or third measure of connectivity at network level, and it looks into the presence of existing number of links as compared to the possible number of links. So, it is almost similar to alpha index, which looked into the existing number of cycles as compared to total number of cycles, and alpha, beta and gamma in a way are highly correlated amongst each other. So, in here in gamma index also we see that gamma index can vary between 0 and 1, it cannot be more than 1. So, in here we see the number of vertex is same across these 4 graphs, whereas the number of edge keep on increasing. In here we will reach a gamma index of 1 if the number of edge reaches 15. So, in here as per the given graph D, which has the highest number of edge of 11, the gamma index is 0.73. The fourth measure that we will be discussing is related to network density. We have mentioned about network density previously, where we are actually measuring the overall length of edges or length of a network in terms of unit area of surface. For example, the length of road network per square kilometer, the length of rail network per square kilometer. So, the higher the value gets, the more developed a network is. In relation to the network density, we have another measure which is known as the average shortest path length. So, this is a measure of efficiency of a network, and this is evaluated or calculated by looking into the average number of stops that is needed to reach between two distant nodes. In this particular graph, the existing actual distance or length of each link is not known. It is also not mentioned whether this is drawn to scale. So, we have to assume it is not drawn to scale. So, within this network we can however look into the number of links that is necessary, that needs the number of stops between two distant nodes. So, the distant nodes as given by this table, it shows that node 1, node 6, 7 and 8. So, with respect to node 1, node 6, node 7 and node 8 are all having distant or the most distant nodes. So, similarly with respect to node 2, we find that node 6, 7 and 8 are again the most distant. With respect to node 3, the node 8 is the most distant. So, we will be using the same example to calculate other measures. So, if we sum up the row total for this table, we will be getting a certain measure that indicates which nodes are having a higher value in terms of the network, but this will be explained further once we discuss the next slides. So, using the same example, here we have presented the connectivity index. So, before we discuss the connectivity index, let us discuss another a node level connectivity measure, which is known as order or degree of a node. Degree of a node is actually the number of links attached to a node. So, in here we find that node 2 and node 5 are having the highest degree of 4, whereas node 4, node 6 and node 3 all have a degree of 3. This can be easily calculated from this connectivity matrix. The connectivity matrix present in here actually shows whether a direct link exists between any two nodes. So, if we sum up the row total of this connectivity matrix, we will be getting the order of each node present in here. This connectivity matrix is also known as adjacency matrix. So, we see that if we add up the row total of say row 5 or row 3, we can clearly again calculate the order of the nodes, order of node 5, order of node 3 and so on. Using the same example, again we will be looking into another measure of connectivity at node level, which is known as Schimble index or nodal accessibility or nodality. So, this actually is a measure of accessibility where the overall sum of length of all shortest path connecting one node with all other nodes in the graph is given. So, ideally the nodes having higher value are actually more distantly placed in a graph as compared to the nodes having lesser value in terms of the nodality or Schimble index. The inverse measure of Schimble index is known as closeness centrality. So, the lesser value a node has in terms of Schimble index, the more central that node is in terms of the graph. So, if we here we have actually included the distance or of each link present in the graph, and we have calculated the shortest path between each node and every other node in the graph. In this given matrix, the distance actually they are the shortest path present between each node. So, there might be say two alternative paths are present between a pair of node. Here only the shortest amongst the two are taken. So, if suppose two nodes are having the alternate paths are also having same value, in that case also any one of them is been included in here. So, if we look into the summation of row total for this particular matrix or this Schimble index, we find that node 7 and node 8 are having the highest value. Node 7 and node 8 having highest value in terms of Schimble index indicate that node 7 and 8 are actually not very centrally located in this graph. On the other hand, when we look into node 4 and node 6, their values are actually the lowest or the next lowest value in terms of Schimble index, and they should be more central to this network. This particular explanation or this particular graph can be explained further by looking into another measure of connectivity at node level. So, this is the betweenness centrality. So, betweenness centrality actually measures the accessibility which is given by the number of times a node is crossed by shortest path in a graph. So, shortest path between any two distant nodes or any pair of nodes if we calculate, and the number of times that shortest path, if a node is crossed by more number of shortest paths, it is more central to the network. So, previously while looking into the Schimble index, we have measured the closeness centrality that also looks into the whether certain nodes are more centrally located. So, betweenness centrality is also looking into a similar characteristics of a graph. So, we have used the same example as in previous slide, and we see that in here the links which are represented in red is actually the minimum spanning tree of this particular network. In this minimum spanning tree, we have seen that node 4 and node 6 are both having a order of 3 in this network, that is also included as a part of minimum spanning tree. We can conclude this while looking into the other measures such as Schimble index or connectivity matrix, that if a node ideally has a higher order, it usually takes a more central position in terms of minimum spanning tree, in terms of say it will ideally it should have a better betweenness centrality or better closeness centrality. But it should be marked here that though node 4 and 6 are having an order of 3, in this graph we have 2 nodes which are having an order of 4. So, ideally they should have been more central to this graph, but it is not true, and it becomes clearer when we use Schimble index instead of simply looking into the connectivity matrix or looking into the average shortest path. When we actually look into the distance between each node in terms of Schimble index, we can clearly identify which nodes have a more central role to play. So, in the last slide we have seen that node 4 and node 6 were having the lowest value in terms of Schimble index, and in here also we see that they play a more central role in with respect to this given graph in terms of minimum spanning tree and also in terms of the shortest path presented on the left hand side of the slide. So, we see the distant nodes are selected based on the average shortest path that we have discussed 2 slides or 3 slides back, and these are the actual shortest path present. So, within the shortest path present, we see that node 4 is the one which is crossed or which is used maximum in all these shortest paths. So, node 4 is having the most centrality or most betweenness centrality with respect to this graph. So, while we have discussed these measures related to connectivity, particularly through network analysis, we see that within this given graph, node 4 which has an order of 3 is actually having the best connectivity in terms of betweenness centrality as well. Previously, we have also seen that with respect to Schimble index also, node 4 is having the best value in terms of connectivity with respect to the whole graph. Now, when we move forward to a measure of accessibility which is combining connectivity along with a certain destination related goal or attractiveness. In using the same graph, using the same network with same distances, now if we include these population which can act as attractiveness for each of the nodes, then we need to see how accessibility gets affected while looking at the connectivity aspect, also while looking at the attractiveness aspect. In here, potential accessibility is actually a summation of individual attractiveness at a location as well as attractiveness of other locations divided by the respective distances. So, for example, if we have to calculate the potential accessibility at say node 2, then we have to consider the overall attractiveness of node 2 given by the population at node 2, and we also have to find out the distance led or distance the population of all other nodes from node 2 divided by their individual distances between node 2 and those other nodes. This will be made more clear when we look at the next slide. If we look at this slide, we see that in the previous slide we had looked at respective population at each node. Previous to that, we had calculated or looked at the connectivity matrix. We had looked into the Schimble distance or the Schimble index of this given graph, and in here in this slide we have the Schimble distances respective to each point or each node. In the potential accessibility, if we look into the column total for individual nodes given in here, for example, if you can follow the cursor, if we look into these column totals, then these are the potential accessibility of each node. Now we can well see that the potential accessibility of node 4 is the highest in the given graph. Now, is this only because of the connectivity aspect? Because node 4 did have the best connectivity as given by the Schimble distance in here only. So, in here the Schimble distance respective to node 4 is the lowest. It means node 4 is providing the most connected node in this network. Also, a point to be noted is population wise, node 4 is having the most population. So, in a combination, node 4 is having the best potential accessibility. Now, if we look into the other nodes, we will see that with respect to population, following node 4, the next node having highest population is node 1, which in here also has the next highest potential accessibility. Not the next, has the third highest potential accessibility, which is node 1. So, in here actually we see that it is not a very simple way to predict that if connectivity runs in a certain way, or if destination attractiveness given by say number of job availability, number of population or number of other opportunities that is available at each node, if we know these, then we cannot automatically predict that the combined accessibility will be of this value, because it is not as straightforward or as linear as we think it will be. So, in here we can see that the node having lowest potential accessibility is node 7. Now, node 7 is not having the lowest population, that is node 3. Node 7 is having a low connectivity given by the Schimble distance. A similar node having very low connectivity is node 8. It is also having low potential accessibility, because population wise they are again not having the highest population in the given network. In the given network, node 5 is having a population which is mid range. It is having a Schimble distance, which means it is better connected. In node 5 we do not see, node 5 is kind of ranging midway with respect to potential accessibility. So, when we are calculating potential accessibility, say we can give an example of node 1 or node 2, we see that with respect to node 2, if we look into the distance between node 1 and node 2, and if we look into the respective population of node 1, then we divide that population at node 1 by the distance between node 1 and node 2 to get the value of each cell in that particular column with respect to node 2, and thereby we calculate the total potential accessibility. So, in here we have shown or given an indication about how connectivity can be used to find out accessibility, because when we are discussing about accessibility, it is just not a network driven measure, it is just not dependent upon the distance or the time or the number of opportunities separately. It is a combination of all these factors taken together. And with that, we will end this lecture. Thank you for your attention.